Unfortunately, lecture 8
all the sound.
does not work the sound. Sound does not sound.
Oh, there is just one lecture where the sound is corrupted, right? Okay, hopefully this one is working. So anything that you say from now on is forever recorded on the internet. Let's see. Okay, so this is lecture 20. And we'll talk a little bit more about the Fourier transform. Part 2. So, last class, we started by defining the Fourier transform of an L1 function. So if I have an integral function Rd, the Fourier transform of this function, f hat of xi a vector on Rd as well, it's just the integral of Rd, e to the minus 2 pi I x xi, f of x dx. So here x is a vector in Rd, so is xi, and here, of course, I mean the inner product. This is the basic definition. First very nice thing that we proved last class is that I have this so-called Riemann-Lebesgue lemma. Which says that, well, if f is in L1, then the Fourier transform is a continuous function that goes to 0 at infinity. We denoted this space by C0 of Rd. So continuous functions that vanishes at infinity. This is very nice because this somehow improves a little bit on the very basic estimate that you get to estimate the L1 norm. I'm sorry, the L infinity norm of f hat. So if you just want to know something about the absolute value, and you have the absolute value of an integral. So whenever you have the absolute value of an integral, the very, very, very least thing that you can do is to move the absolute value inside to estimate. If you don't know how to do better, you can do at least that. And of course, this will give you the estimate that the L infinity norm loses to the L1 norm of f, because this guy is a complex number of modulus 1. Okay? But as I told you in the last class, we are here to do the business of estimating integrals better than this trivial estimate. So one of the issues in harmonic analysis or Fourier analysis that usually pop up is that we have to understand oscillation a little bit better. Okay, just not with a trivial estimate. So this integral here has a lot of oscillation in this kernel. If xi is very large, you can see this is a very large guy, so this will oscillate even when x is small. And this result is a first capture of this phenomenon. Right? So this function is not only bounded, I know that it's bounded trivially. It's not only bounded, but when xi goes to infinity, this guy goes to 0. And as I said, we said in the last class, this is a very, very nice example of, say, the power of the tools that we have learned in analysis, right? So to do it for L1, this is enough to do it for the dense class. Take the simple functions, or the step functions, the linear combinations of characteristic functions of cubes. Well, if I could, since this is a linear operator, I could just do for one rectangle or one cube. Since we know how the Fourier transform it behaves very well with respect to translations and dilations, I simply have to do it for just one cube, the unit cube centered at the origin, because then I can translate and dilate as I want. And then, since just take the cube centered at the origin, since it has a product structure, and this Fourier transform behaves nicely when you have a function that has a product structure, it just splits into the product. So all you have to do is to understand this problem in one dimension for the unit interval centered at the origin. And then you just compute the Fourier transform. And it sine pi x over pi x if you. Okay? So we saw some basic properties also in the last class that I told you to think about how to prove it. But especially with respect, this is the first one. Well, how the Fourier transform behaves with respect to linear transformations, especially dilations, and rotations. So very nice. We saw that it takes the convolution of two functions, and if I take the Fourier transform, it takes into product on the other side. And there is a nice relation between multiplication by polynomials on the physical space and differentiation on the frequency space. Okay, so but it actually before that takes translation on one side into what we call modulation in the other side, and it takes multiplication by polynomials in one side to differentiation in the other side. Okay, so these are like very, very nice properties that we have from our Fourier transform. So let me give you one example of a nice thing that I wanted to mention to you. Okay. Suppose I tell you this. Suppose that for each function, let's say C infinity of compact support on RD, one has the estimate. Fourier transform, and say LQ of RD loses to a constant times the norm on LP of RD. Suppose you had this. And my question is, what should be the relation between P, Q, and D? Okay, for a universal constant C. Okay, so suppose that for you have a universal constant C, which may as well be a C that depends on D, P, and Q. That's okay. But that for any function f, you have this estimate here. The LQ norm of the Fourier transform loses to the LP norm of f times this constant C. The point is that the constant C does not depend on f, okay? And my question is, what should be the relation between P, Q, and D? You'll find this sort of problem many times in your life. I am not saying that this is true for any P, Q, and dimension D. So understand my question.
But it happens for infinity and one.
Yeah. Here, P and Q are between 1 and infinity, let's say. What I'm trying to tell you is that if such an inequality holds, can you give me some non-trivial information about the exponents, P, Q, and D? Okay? So every time that you encounter some sort of inequality like this in your life, say somebody tells you that one object on the right-hand side controls another object on the left-hand side by a universal constant. It could be a Sobolev inequality that you have the gradient here controlling the LP norm of a function or something like this. And this is a global estimate, so this is the key. Right? So this is what we call a global estimate. This is not local. This is something that holds when you take the LP norm on the entire space and a function on the entire space.
PQ are conjugate numbers or just any PQ? Conjugate.
We will prove that P and Q that have to be conjugate numbers. I will prove to you that they have to be. But in principle, I'm just starting with the question. Suppose that an estimate like this holds for some P, Q, and D, the dimension D. What should be the relation between these guys, right? Suppose that a global, and whenever you have a global estimate like this, there's a very, very interesting, well, I won't say trick, but a very interesting observation that you have to make to give your first step. And the observation when you have a global estimate is that it has to be dilation invariant. Okay? So you have to understand the meaning of this thing. So if an estimate holds like this, for any f, then it has to hold, so this holds, if I given any delta bigger than 0, the estimate has to hold for the function f delta of x, which is, I will just define as, say, f of delta x. Okay, so if this holds for any functions, infinity of support, compact support f, the estimate has to hold for the function f delta that I'm defining here, which is just f of delta x, where delta is a fixed parameter, bigger than 0, fixed real number. Okay? So the estimate, let's just plug in. So you must have f delta hat in the LQ norm less than or equal than a constant times the LP norm of f delta. And what you want to look for is how both sides vary with your parameter delta. Okay? So let's just compute. What is the right hand side? Let's just compute here. What's the right hand side? The LP norm of the function f delta of x is just integral of f delta of x to the p dx raised to 1 over p, correct? And then this is just the integral of, well, f of delta, by definition this is f of delta x to the p dx raised to 1 over p. Now I change my variables here, I make delta x equals y. This becomes the integral of f of y to the p. dx becomes dy over delta to the d, because I am in dimension d, okay? 1 over p. So at the bottom line, this becomes what? Delta in the denominator to the power minus d over p times the LP norm of f. Is that okay? Okay, so this guy here is just c delta minus d over p times the. This holds for any dilation. So the LP norm of a dilation is related to the LP norm of the original function by a certain dilation factor. We have already seen this thing, for example, when we did the approximations of the identity. So if we dilate correctly, we preserve the norm. But anyway, so let's see how the left-hand side behaves.
Just to replace.
Well, we have seen that one of the basic properties told me how the Fourier transform behaves with translation. So if you remember correctly, f delta hat of c, if my function is just f of delta x, this will be 1 over delta to the d, f hat of c to the d, c to the delta. Okay? This is by the basic properties that we saw last class. Then I just calculate the LQ norm. Good, so the LQ norm of this f delta hat is just the integral in our d over this object. So let me just put it already here. F hat of c over delta. This whole thing to the q, dc, so to the 1 over q. And then you just change your variables again. C over, you call it c over delta of w. Let's see what we get. We get rb. I'm going to keep this guy here, 1 over delta to the d. F hat of w to q. dc is delta d dw, and the whole thing 1 over q. So what you have is what? This is equal to the LQ norm of f hat that appears here, multiplied by a certain power of delta. Which power is this? So I'm going to have here minus d over Q, with this raised to the, no, I'm gonna have,
T.
well,
This is T.
yeah, I'm gonna raise to Q and then 1 over Q. So I'm gonna have delta to the minus D, correct? And the other one will be this one, D that I'll just raise to the Q. So plus D over Q. If I did the computations correct. So you end up actually finding this inequality. So if this inequality is supposed to hold for all functions, f, just fix one f, it holds. It has to hold for all the dilations, f delta, but then this implies that this inequality here in the bottom has to work. Now, you see powers of lambda appearing on both sides. What has to happen with these powers of lambda appearing on both sides?
This should be inside that.
Your lambda is any number between 0 and infinity. The powers to which the dilation factor lambda are raised to, they have to be equal. Because if the power is bigger on one side, then you could send lambda to 0 or infinity to break the inequality. Okay, so this is my point to you. If I tell you that lambda raised to a certain quantity alpha times A loses to lambda to a certain quantity B beta times B for all lambda bigger than 0, what you do? This is essentially saying that lambda to A minus B, A loses to B. Now, if this exponent here is positive, if alpha minus beta is positive, you will just send little delta to infinity, and it would break this. This would be untrue. If alpha minus beta is negative, if it's minus 100, you would send lambda to 0, because then it would invert, and it would break this inequality in the same way. So the only chance for this to hold for all delta bigger than 0 is that if these two exponents are the same. Okay? So then, the two exponents here, minus d plus d over q, has to be equal to minus d over p, which if you divide by d, you just obtain that 1 over p plus 1 over q has to be equal to 1. In other words, q must be 2 prime. Okay? So, I don't know if such an inequality holds, but if it holds, it has just one chance that this exponent q is p prime. Okay, so the only chance is that f hat, p prime loses to a constant times f, p. That's my only chance. We have proved that no other possibility may be true. It's just false. I am not saying that this is true, but I have eliminated all the other possibilities, okay? So you may find some problems like this in your life if you're working in analysis or PDE or any other topic related to this. Whenever you have a global estimate, first thing you should check is for the dilation invariance of this estimate. So if it holds for all the functions, then there is a dilation parameter that you can multiply both sides, and these things have to be dilation invariant. You cannot depend on these things. And you find the relation between the exponents. All right? Good. Now, is that clear? This is very interesting. I put online earlier today a little bit of a homework 5. So you can take a look at, you don't have to deliver, just take a look and study for the exam. But one of the questions that I put is something like this. There's a slightly variation of this question, that if you even have, if you multiply your function f hat by a certain power of c to alpha, and here you multiply by a certain power of x to the beta, what is the relation between alpha, beta, p, q, and d that may, such that this may hold? Okay. So
does such an estimate exist, or?
Now, let's come back to the following fact. So my next question is, okay, we have eliminated to this possibility, right? Or less than p, less than infinity. And I may ask you, is this true? Is this true? Well, we have seen that it's true in one case, right?
Be equivalent.
So we have seen that we have, in fact, we have seen that f hat in L infinity loses to f in L1. That is awesome. That is one case of one manifestation of this estimate. Then we will prove later today. We will prove that the Fourier transform is an isometry in L2. That preserves the L2 norm. Okay. Now,
So, is there an interpolation theorem that gets this?
yes, and I'll just mention to you because I think it's important. I won't have time to discuss, but maybe we can take a look at the proof. But there is some interesting interpolation theorems in analysis, and this one is called this Rees-Fourier interpolation. And this is a very beautiful result. You may want to take a look later. The proof uses a little bit of complex analysis, what they call three-line or three-circle lemma, if you remember this fact. But this is essentially something like this. So suppose T is defined in a dense subspace of LPs, if you want. Suppose your operator T is defined in a dense subspace of LP is a linear operator. Okay. Suppose it is bounded in two LPs. Okay, so suppose your T from LP1 to LQ1 and T from LP2 to LQ2. Suppose that these are bounded. That is, that there exists constants such that T of F in Q1 loses to a constant C1 F P1 and T of F in Q2 loses to a constant C2 F P2. Okay, so suppose that your operator is bounded between two guys. So one thing to visualize this, one way to visualize this is that if you write in two x's here, you write a little square, and you say that this is 0, this is 1, this is 1, this is your 1 over p axis, this is just your 1 over p axis, and this is your 1 over q axis. Okay. So I'm taking here point P1, Q1, and another point P2, Q2. So this is 1 over P1, 1 over Q1, 1 over P2, 1 over Q2. And the conclusion of this theorem, if you have an operator that is linear, and it's bounded from, say, one LP to another LQ, and another LP to another LQ, in the sense, then for every point in this line here, that connects these two guys. So for every PQ such that 1 over P, 1 over Q is a linear combination. It's as a, say, theta, 1 over P1, 1 over P1, and minus theta, 1 over P2, 1 over P2. For 0 less than or equal than theta less than or equal than 1, we have that T of F. We may as well call this P theta, Q theta, P theta, Q theta. T of F in Q theta loses to, it is a bounded operator. And you can even give an estimate on the constant. So if the constant here were C1 and here it was C2, what you have here is just C1 raised to theta C2 raised to 1 minus theta. Let's see if I'm doing this correct. So if theta is 1, you are essentially at this point, you get the constant C1. If that is 0, you're essentially at this point and you get this constant C2. Good. So this is the estimate. So, again, if you have a linear operator, and here linear is crucial, if you have a linear operator that is defined in, say, a dense subspace of these LP guys, could be just linear combinations of step functions, or the combination of characteristic functions of rectangles, or Schwartz class, or same infinity of compact support if you want. If it is bounded in 2 points in the square, then it's bounded in the line that connects these 2 points. Okay? There is this interesting normalization here. You don't take PQ, you take 1 over P, 1 over Q. So if it's that, if 1 over P, 1 over Q is a linear combination of your 2 pairs, then you're okay. So how does this translate?
I'm just having a question. What is the role of the first P in which T is defined on a dense subspace of fit with the other Q's and B's? That just this B doesn't appear again in conclusion.
It has to be.
So what is the significance of being defined on a dense subspace here?
So if you prefer, so let's just put, T is defined in, let's say, in LP1 plus LP2, if you want. Just the set of functions f plus g with f belonging to LP1 and g belonging to LP2. I was just saying that you get an operator that is defined in a dense subspace of all LPs, if you want, just to be simple. Could be, but here's perhaps more illustrative. Okay, so suppose your operator is defined in the subset of these 2 spaces. Functions that are in LP1 and functions that are in LP2. And then every function, well, if you consider the space, the sum of these 2 spaces, well, this is the space of f plus g, where f is here and g is here. So you can actually show that any LP in between actually lies inside here. You can just take an LP function with P between P1 and P2 and just truncate your function. Let's take 100 and say, consider the values which are less than 100 and bigger than 100. Just truncate it. And then the less than 100 will belong to this space and the bigger than 100 will belong to this space. It's not hard to prove that. Okay. Does that answer your question? I just want my operator to be defined everywhere that I use it. This is what I want. You should not worry too much. That's not the point of the theorem. Because if I just put, okay, suppose that T is defined in LP1. Suppose that T is defined in LP2, you might ask, oh, okay, but why is a T defined in somewhere in the middle? In principle, you don't know. Okay? But in this case here, where am I in this situation? So if I put this square, this point here would be, if this is the line 1 over P, this is the line 1 over Q, this point here would correspond to what? The P1 and the Q infinity. So 1 over P would be 1, 1 over Q would be infinity, 1 over Q would be 0. So this is the point. And the other point is the point 2, 2, which is kind of right here in the middle of the square. So what I'm saying is that this operator here is then bounded in the line that connects these points. Okay, so this implies that f p prime loses to a constant f LP just on the line that connects these 2 points for 1 less than or equal than p less than or equal than 2. You can even, if you want, get some information on this constant here. Because I'm telling you that if you have an inequality on P1, Q1 with constant C1, and P2, Q2 with constant C2, then you have information on the interpolating constant here in the middle. So here I have the inequality with constant 1, in one of the points, and with constant, say 1, 2. Here is actually an equality. So you could actually conclude that this is true with constant 1. This is called the Hausdorff-Young inequality. That the LP norm of the function wins against the LP prime norm of the, Fourier transform for p between 1 and 2. And for the rest of the p, so we already knew that the inequality could only hold if p and p prime were in these positions. I'm telling you that it holds between 1 and 2 because of Plancherel's result that we'll prove in a minute, and there is Turing interpolation theory. And you can actually prove that it does not hold outside of this. So I'll leave you as an exercise for you to think about that does not hold for p bigger than 2.
Range?
P bigger than 2. You can find counterexamples for that.
Sorry, what doesn't hold?
This.
For what? C equal? C
For any C. The inequality does not hold. This inequality does not hold for p bigger than 2. Okay? It's not so trivial to prove that. Go and research online how to actually construct a family of counterexamples. Good. This is just a little bit to illustrate some of the facts that would follow, but I want to go back to, we are defining the Fourier transform in L1. I haven't actually told you how to define it in L2, because so far what we have is just an integral that absolutely converges if your function is integrable. Okay, so this was just a brief detour, nice stuff that I think you should know. Let's go back. Let's go back to where we stopped in the last class.
Do we have something for this direction?
That-
Inequality this direction. Do we have some constant which is?
Well, you will just prove the Fourier inversion, right? So when you have Fourier inversion, you have the opposite. You have the opposite inequality in the opposite range. Well, no, not exactly. So what you have is, so what you have is this. You have the same Hausdorff-Young inequality, if you want. This is what you have. You can change the roles here of f and f hat if you want, because of the Fourier inversion formula that we're going to show. But only this. You don't have more than this. Okay? So this LP norm controls this guy controls this one, but this one doesn't control the f hat anymore, because if p is between 1 and 2, p prime now falls out of this range. Unless you are, of course, at the point 2, then you have all equalities. Okay. So last class, we ended up proving the following proposition.
So can we prove that it's an isometry only on 2?
I think we can, yes. We can certainly
This
do
would
that.
prove that the inequality cannot hold for any. This would prove that the inequality cannot hold for p bigger than 2. Because then we'd have a two-sided inequality, which would be an equality. So if this is true, then for two values of p, one and its conjugate would have the equality. And this would prove that for p not equal to 2, this is an isometry. Right?
I'm not sure I understand your question. So you wanted to prove that this doesn't happen,
If it happens for any other p, then
that this does not happen for another p,
Yes.
different than 2. And I tell you, this doesn't happen. Just take an example, Gaussian, for example, and compute both sides as different.
yes. So
It will lose, but it's not going to be equal.
yeah, for p bigger than 2, if we have any value for p bigger than 2, then we'd have it for the conjugate.
Okay, what I'm saying is that there's no constant c. It could be a bigger constant, a million, such that this operator from LP to LP prime is bounded for p bigger than 2. Okay, it's a different question. Of course, you can try to start proving that this doesn't happen with constant 1, that's okay. But you can try to, there's a different thing to prove with constant 1,000,000. Okay, good. It is actually a very interesting question to see, hey, this sort of inequality here, we have proved that it holds with constant 1, just out of curiosity. We have proved that it holds with constant 1. But I ask you, is there any chance that it could hold at the constant c smaller than 1? Again, independent of f. Okay? So just as a curiosity, if you want. So c equals 1 works in the Hausdorff-Young inequality. But is this the best that we could do? Can we prove it with a smaller constant? Can we actually calculate the operator norm? Because this is an operator, right? This is an operator t from LP to LP prime. And what we're asking is, what is the operator norm that we have learned? And the operator norm in this case is, in fact, the operator norm, or the best constant that you can put there, is actually c. Let me go with the p to the 1 over p over p prime, 1 over p prime raised to p over 2. This is the answer. Just when p is 2, of course, is 1. When p is less than 2, so for example, if p were 1 in this case, you get something smaller than 1. And the norm is realized when f is a Gaussian. Okay, so the operator norm here is realized when the function f that you put here is a Gaussian. This is a result of 1975.
And how do we get the estimate?
So this is the constant. When you plug in a Gaussian, this is what it gives. You know how to compute this side, you know the Fourier transform of a Gaussian is itself, you just compute it and you give this one. So it's a matter of proving that the Gaussian functions are essentially the best ones that you can plug in for this inequality. Good. Let's do the Beckner. Now, okay, there's still a little bit of ground to prove Plancherel's theorem. It's an isometry on L2. It's one of the goals for today. Proposition we ended up proving on the last class was this multiplication formula. That is, if f and f hat, well, if f and g both belong to L1 of RD, then we have that the integral of f of x g hat is just equal to the integral of f hat g, right? So you can just move to Fourier transform to the other side. The proof is simple. It's just to open up one of these Fourier transforms and use Fourier. Things will be absolutely integrable because both functions are in L1. we'll be done. Okay. This was the last result we proved in the last class. So the first result that I want to prove today is the following. Is the so-called Fourier inversion formula, which is the following. So let's first prove in this setting. If f and f hat both belong to L1, we have f of x is equal to the integral over Rd of e to the 2 pi I x c f hat of c dx for almost every x in Rd. So the statement is that you can, once you know f hat, you can essentially recover your function f by almost applying the Fourier transform again. This is just a slightly different operator. Remember that we defined our Fourier transform with the minus here. So this is sometimes called the inverse Fourier transform, now with the plus. And if f and f hat, so I'm assuming that f and f hat are integrable, we have that f of x is just the integral of e to the 2 pi I x c, f hat of c dx. And again, this is important for almost every x in Rd. Because you may start with an integrable function, just integrable. So if f is just integrable, you could modify it on a set of measures 0, and that would be the same function. Now you pass to the Fourier transform f hat, and f hat is now a continuous function. And I'm assuming that f hat is integrable. So when I do this operation with f hat, the Riemann-Lebesgue lemma applies. So I get, from this operation, again, a continuous function. But since my function f was just integrable, so I can only say that they agree almost everywhere. So in other words, f would have a representative that is written like this. Okay. Good. This proof is actually quite interesting. And what we want to do is that we want to make use of the multiplication formula on the previous line. So what I would like to do is just to use that I have f hat here, this would be my g, and I would like to change the roles of the hat. Well, you could argue that the Fourier transform of this guy is just the function delta, if you want, if you know a little bit more of distributions, but this is not within what we have done before. So let's find it a proper way to do with our tools. And since this function, so the idea is to use this formula that I can fluctuate the hat between f and g, but only if f and g are integrable. So here I have f hat, which I'm assuming is integrable, but I have this crazy function here, which has absolute value 1, that is not integrable over Rd, right? So what's the idea? I force it to be integrable. Let us force it to be integrable. So let us define phi t of c, put the parameter t here, so for t bigger than 0, let me define phi t of c to be e to the 2 pi I x c, this guy, phi t of c, but that's okay, times e to the minus, so what do I want? What do I want here? Maybe I want this thing, p c squared over t squared. Let's do this. Let's do this, yes. Do I want this? Maybe not. Let's see if this is what I want. Up, 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 up. Maybe this. Let's try this. Let's try this function. Okay? Good. If I define this as phi t of xi, what would be phi t hat of x, of y, if you want? We already know what the Fourier transform of this guy is, don't we? So let's just write what it is. It's e to the minus pi y squared over, so it's e to the minus pi y squared over t squared. Whatever lambda, remember I had a lambda here, I put a lambda on the bottom. Lambda here is t squared. And here I have 1 over lambda to the d over 2, so I got here just 1 over t to the d. But now what happens with this? This is like a modulation on the side. On the other side it becomes a translation. Okay? So this will be y minus x squared. Right? So if I have 2 pi I x c f of c, and I want the Fourier transform of this guy, well, Fourier transform will be e to the minus 2 pi I c y, and then it will be appearing y minus x here. Good. So this is the Fourier transform of this guy. This guy looks similar to you, doesn't it? You have seen this guy before, I suppose.
Yes, it is Q 5. The only did for approximation of the.
So from the multiplication formula, now I can apply the multiplication formula, right? And I can apply it like this. I can apply integral in Rd. I can say that I have phi t of c, f hat of c. Now I have no problem. F hat is integrable by hypothesis. Good. Phi t of c is integrable because although I have something of modulus 1, this decreases fast. This is a Gaussian. So this is something equal to the integral of phi t hat of x f of what we're calling here y. Right? So this is the multiplication formula. I move the Fourier transform to this guy. Okay, so what is this? Now this is just integral of, let's see, 1 over t to the d. So you may call this function, well, okay, is this what I want? Yes.
This is equal to 1 over TD.
This is...
Maybe we denote this function e to the minus t y minus x squared and t squared. We need to denote this function, maybe take a psi or something. This is a approximation to the ideas.
Yeah, so if I want to call, if I call this function, say g of y to be, problem is my t's is a little bit bad. So gt of y, if I just call it 1 over t to the d, e to the minus pi y squared over t squared, I can just call this function, right? So this will just be g, which is my approximation of the identity, right? Of y minus x, or of x minus y, f of y dy. Okay? Which is just gt convolved with f at the point x. Now this g is just an approximation of the identity, so this gt here is just 1 over t to the d phi of y t, where this phi function is just e to the minus pi y squared. Okay, good. So I know I can now send my t to 0. I know I can send my t to 0. So let's just do it here. On this side I have RD e to the 2 pi I x c e minus pi t squared. What I will do now, this is an identity. What happens when I send t to 0 in this one? Yeah, so this is just dominated by 1, and this is just something integrable. So here, the integrand is dominated by this guy, which is integral. So I can pass t to 0, and by dominated convergence theorem, this goes to the integral of Rd of e to the 2 pi I x c f hat of c dx. Now what happens when t goes to 0 here?
So where is the t in this? Where is the t? I don't see any t.
T is here.
Ah.
T goes to 0, this goes to 1. This is t, I put this t here to make this decay. But at the end I want to make my t go to 0 and to get back to what I had before. So this goes to this side. And then when t goes to 0 here, what happens with this guy?
Almost 11 points.
It goes to f of x at all Lebesgue points here. In particular, almost everywhere. So this must be equal to this almost everywhere. Suppose you didn't know the result about the pointwise convergence. You could still use the easier result of L1 convergence, because you know that this converges in L1 to this function. So this converges in L1 to this function. There is a subsequence that converges almost everywhere. So this function must be equal to this almost everywhere. But since we already know the most powerful result, so let's just keep it. Is that clear? So this completes the proof of the Fourier inversion and uses nice properties of the approximations of the identity that you know. Good.
Is this the most powerful result in this regard?
Which one?
The one where it converges on all the big points?
Yeah, these approximations of the identity, remember, if you have a kernel which is radially decreasing or radially majorized by something integrable, the convergence is pointwise at all the Lebesgue points.
Feels nice to know this theorem.
It feels really nice, yes. It feels, you know what feels even nicer? To know how to prove it. But to know and to know how to use it is already very nice. 99%. It's more important to actually know it and know how to use it well. Then it's good to have proved once in your life. So you are worthy of using it. Good. So we are good. Now I want to just make some remarks. So let me make some remarks on this. So the first remark is actually, suppose that in this proof, in the course of this proof, you have the following fact. You have that if f belongs to L1, if f belongs to L1, what do I want to say? If f belongs to L1, this side, I want this to actually work as a corollary. Corollary, I want to put it like this. Corollary. Suppose f belongs to L1 of Rd, okay, that f hat is bigger or equal than 0, and that x equal to 0 is a point of continuity of f. So now let's work under this hypothesis. You have an integrable function f, you have that 0 is a point of continuity of f, and you have that f hat is bigger or equal than 0. I'm not saying that f hat is integrable anymore. Then the conclusion is f hat is integrable and therefore the Fourier inversion applies. Almost everywhere. And the second one is that at 0 it actually applies. Okay. And the proof essentially follows from this argument here. So let me state that this is a very interesting corollary. Again, I'm assuming that my function is integrable, and I'm changing the hypothesis that I had before, that f hat was integrable for the fact that f hat is non-negative, and 0 is a point of continuity. Then, in fact, if this is true, then f hat is integrable, and therefore the Fourier inversion holds almost everywhere, as we have proved. And it actually holds pointwise in the point x equal to 0. Now, the proof is essentially hidden right here. You can do the same thing, consider this kernel, consider this, and consider this identity. This is an identity that's okay. Why? Because f is integrable. Remember, to have the product formula, you needed to have two functions were integrable, f and g, right? So you have f, this function is integrable, and this function phi t here is integrable too. Okay, so this is an identity. So let's just get this identity here that holds for any point x and apply it in x equals to 0. Okay, so let's call this star. So you just apply star at x equal to 0. And then you would get integral over rd of e to the minus p t squared, c squared, f hat of c. C would be just the gt convolved with f at 0. Okay, applying this identity here at x equal to 0. Now you already know that when you send t to 0, what happens with this side? This side here converges pointwise to f of x at all the Lebesgue points, but I'm assuming that 0 is a point of continuity of f, therefore Lebesgue point, so this will certainly converge to the value f of 0. And when I apply the limit as t goes to 0 to this guy, what do I have?
Given by dominated conversion.
I have this by which theorem? Not dominated convergence, because this is not a
Monotone.
by monotone convergence. This is a positive function, and this is something that goes to 0, goes to 1 monotonically. So this, whatever is inside is increasing, right? I don't care where it converges to, it might converge to infinity, but it will converge to whatever this is. It's a monotone convergence. So when t goes to 0, this converges to this. When t goes to 0, this converges to this, which is a number. Therefore, this implies that f hat is in L1, because the integral of f hat is the integral of the absolute value of f hat. Okay? And, moreover, this is an identity. Okay? And 2 holds. All right? Good. So we're now in position to prove one of the highlights of this class, too. Plancherel's theorem. Do we have questions up to here?
Sorry, why is f hat isn't L1?
This is an identity. For any t, I have this is equal to this. Okay? When t goes to 0, this side goes to this number. Do we agree?
Yes.
When t goes to 0, this side goes to this number. So this number is equal to this number. In particular, this number is finite. Since f hat is positive, this number is just the L1 norm of f. Okay? So in particular, the L1 norm of F is finite. Inversion formula holds almost everywhere by the previous theorem, and it holds at 0, well, essentially, it's right here. Good? This is slightly subtle. It's not. So in particular, you would have, you would not have to invoke the full power of the pointwise approximation of the identities at the Lebesgue point, but you would have to know how to prove that it converges back to the function if you have a point of continuity. This is all that's using here. Okay, so let's see. So what we want to do now is the theorem, sometimes referred to as Plancherel's theorem, which is the following. So I still don't know how to define my Fourier transform for a function in L2. I only know when I've only worked with the Fourier transform defined on L1. So this is where I live. Yeah. So suppose now F belongs to L1 of Rd intersection L2 of Rd. Suppose we have a function that lies in both spaces. Of course, there may be functions that lie only in L1. There may be functions that lie only in L2. These two spaces are not contained in one another because Rd is not a bounded domain. If you are in a bounded domain, then any function that is in L2 is in L1. But not in an unbounded domain. But now assume that your function f belongs to the intersection of these two spaces. In particular, you can define the Fourier transform of f because it's in L1. Then, let's just say that f hat belongs to L2 of Rd, and the L2 norm of f hat is equal to the L2 norm of f. Beautiful result. Let's see how we prove this. Proof.
Because the effect is in the way, so the next formula follows.
The inverse formula? Well, it doesn't follow. We have proved that the inversion formula holds if we have f in L1 plus something else, So this is not applying the inversion formula directly. There is a very neat argument here. So let's see. And again, we will invoke some things that we have proved in this course. Let me try to start here. So consider g of x. Let me just see if I get this right. F of minus x bar. Just consider this function. Remember, my functions here are complex valued, okay? My functions are complex valued, so I'm taking g of x to be f of minus x bar. Because the Fourier transform has a complex character on there, right? It has e to the minus 2 pi ix, which is a complex number. So all my functions f and f hat in these past two lectures have been complex valued. Let's just choose g to be f of minus x bar. Let's see if this is correct. And I want to consider h to be the function f convolved with g. I want to consider this. What can you tell me about this h? There are some things you could tell me about h, right? So what can you tell me about h? Tell me something. Tell me something nice about h. You can apply Young's inequality to say that h is in L1. H is in L1. You have seen this of Young's inequality, right? So that's good. H in L1 is actually less than or equal than f in L2. G, which is essentially f in L2, right? So which is less than 5. So h is in L1. But remember when we proved Young's inequality, we actually proved a little bit more. This was actually an exercise in your first exam. What happens if you take convolution of two L2 functions?
It decays at infinity.
That's good, but it's also
C.
continuous, right? So h is a function that decays at infinity, and it's a continuous function. Right? Exercise in your example is just to prove that it's continuous, but it also goes to 0 at infinity. So h is not only an integrable function, but it's continuous and goes to 0 at infinity. Good! What else? What is the Fourier transform of h? It's the product of the Fourier transforms, right? What's the Fourier transform of g? Now let's do a side computation here. Try to compute what's the Fourier transform of g. G hat of c is just the integral of e to the minus 2 pi I x c g of x dx, correct? I go here and I raise my g of x and I put f of minus x bar. I go here and I put the bar on top of everybody and I change here to the conjugate. Okay? There's a minus x here. I change it minus x to y and I get the integral of e to the minus 2 pi I y c f of y dy. Correct?
With a
No,
minus?
that's mine.
With a minus outside?
Minus outside?
To the power.
Oh, minus outside due to what?
No.
Because you made a change of variables.
Dx minus
Of the minus dx?
Okay.
There's no such a thing, because if you were in one dimension, you would be changing also the limits of integration.
Okay.
Okay, so essentially when you are in several variables, what pops out is the Jacobian, the determinant of the Jacobian, right? So don't make a confusion for that, so there's no minus here. But what is this?
The Fourier transform.
Fourier transform of f at the point?
C.
C, what else? Bar. Fourier transform of C, Fourier transform of C conjugate. What is this? Just the modulus squared. So in particular, h hat is non-negative. Here's a non-negative function. Here's a continuous function, such that h hat is non-negative and h is integral. We're going to use that. So, from the previous result, the previous corollary, what you have is that h hat belongs to a 1 and h of 0 is actually equal to e to the 2 pi I, well, h of 0 is just equal to the integral of h of c dx, h hat dx. Okay, let's just open up to see what this is. So what is h of 0? On one side, h of 0, so you start with this. H of 0 is just f convolved with g at 0, by definition. F convolved with g at 0 was just the integral of f of x, g of minus x dx, right? This is the convolution of f and g at the point 0. But this is equal to the integral of f of x. Well, how much is g of minus x? G of minus x is just f of x bar, which is just the integral of f of x squared, which is just L2 norm of f squared. Now let's go to the other side. What is this? Integral of h hat. Well, h hat is right here. It's rather easy. H hat is just f hat of c squared. So this is just... And here's your Bunch of errors there. Okay? So now we know how to prove that if a function is in L1 intersection L2, it preserves the L2 norm. Good? Very nice, isn't it? Very, very nice. So, this tells me how to define the Fourier transform on L2. L2 is actually the ambient space where the Fourier transform will actually make more sense. So this tells us how to define the Fourier transform in L2 of order. Because since it's an isometry on a subspace, and the subspace is dense, well, L1 intersection L2 is dense in L2 because all the functions infinity of complex port are here. So you have defined this functional, this isometry on a linear subspace. Well, I mean, to extend it, there's a unique extension which is bounded to the whole L2, right? And the way you do it, in the sense that there is a unique linear and bounded extension. The way you should do is that you take f in L2, you define it as the limit of functions in your subspace. So take f in L2, just take any sequence, say fn belonging to L1 intersection L2, fn converging to f in L2 norm, and define t of f as the limit, as n goes to infinity, of t of fn in L2. Why does this sequence have a limit? Well, you observe that if fn converges to f in L2, then this implies that fn is Cauchy in L2, right? Since that fn minus fn go to 0. But t, then t of fn minus fn go to 0 because it's an isometry. This guy is equal to this. Therefore, t of fn is Cauchy and converges to a limit. Limit exists. And you baptize it to fn. Okay. Professor, I didn't like fn. Can I choose another gn and maybe I can get a different limit? No. Because if you have fn converging to f in L2 and another sequence of your choice, gn converging to f in L2, then, well, f of n minus gn will be Cauchy. So t of f of n minus gn will be Cauchy. T of f of n will converge to the same limit as t of gn. So it doesn't matter how you get this approximating sequence, you get the same t of f. Okay? So it's just the lift. If you have an isometry on this subspace, there's a unique extension to L2. That's a limiting of functions in the subspace. Okay, this object now defined in L2. Now we have defined it in L2. Take any function in L2. Take any convergent sequence in L2 in the subspace and define the Fourier transform of f as the limit of these guys. Right? For example, you can just take f and multiply by the characteristic function of the ball of radius n. Send n to infinity. Just truncate your f. So the Fourier transform of f is defined like this. This is the Fourier transform defined on the space L2. Okay? And since we have defined it this way, it preserves this isometry property in L2. Because this holds for any if you take f, this holds for any fn that converges to f, so this will hold at the limit as well. So this is the Fourier transform as an isometry in L2. Is that clear? Okay.
So the integral comes from L1
Yes.
and it's extended by this isometry, by this relation.
Yes. The original definition of the Fourier transform, I mean, the most basic definition is for an integrable function, right, where things converge absolutely. So if you want to actually describe to me what's the Fourier transform of a function in L2, you have to approximate by functions in L1, in the L2 norm, but by functions in L1 that you know how to compute the Fourier transform, and by this property, these Fourier transforms will converge. Right? I marked here T, I don't know why, this is actually F hat. T is just the Fourier transform I was just considering. What am I doing here? I'm crazy. So it's just F hat. It's just the limit of F and hat.
You were just calling it for general.
Yeah, for any general T, yes, okay. Yeah, anytime you have the situation. Okay, good. Okay, are we good? Good. So let me just. So I have told you how to define. Okay, let's just. Let me see if I can pick your brain a little bit more to just say. So we have just defined a linear operator. Let's call it F for Fourier transform. Sometimes I denote with F, sometimes I denote with the hat. But we have defined this operator F that maps L2 of RD into itself. And that verifies that f of the function f in L2 is actually equal to f in L2. This is the Fourier transform. Okay, so f of the Fourier transform. So I have actually proved that it's an isometry, but I still don't know if it's a, so it's therefore, if it's isometric, if it's an isometry, it's injective, that is fine. Okay. How about surjective? How do we prove that this map is surjective?
Let's take the Fourier transform of, if I'm given G, let's take the Fourier transform of G,
And this goes back to the,
hopefully.
that's one way to do it. Yeah, it's not much hard, but let's try to see if we can do a little bit of our functional analysis here. So let's say f of L2 is a closed subspace, right? It's a closed subspace.
Like this.
And that, well, that's what I want to show. It's a closed subspace.
But don't we have inversion? So f goes to f hat and f hat goes back to f?
That is not true. Okay?
That's not true.
No, this is almost true.
But it's true for L1, which is dense in L2.
Remember, we have the inversion operator is slightly different, right? So what happens is that f goes to f hat, and f hat of x is minus, I'm sorry, it's f of minus x. Okay? Remember, the Fourier inversion operator had a plus sign instead of a minus in the exponential.
But does that matter?
Yes, this is true, but we assume that f and f hat had to be in L1, right? So one way to prove this thing that is surjective is to prove that the space of functions f such that f of hat is in L1 and then f hat is in L1 is a dense subspace in L2. that is okay too. What I wanted to observe with you is just that, so let me just first, maybe as a first step here, I just want to comment that you have, so multiplication formula now is okay. The multiplication formula is okay now if you have f g hat is just equal to f hat g for f and g in L2. Multiplication formula is okay for two functions in L2. Why is that? Well, because it holds for L1, you just approximate f by fn and g by gn, approximated in L2 by functions which are in L1, intersection L2, and this formula holds for every n, and then you pass to the limit. Okay? Okay, so just approximate fn f, so fn in L1, and approximation in L2, and gn approximates g in L2 with gn in L1. Okay. You got to be a little bit careful with the Fourier inversion formula on L2. It will get back the same function in L2. Yes, that's correct. This thing that I wrote here on the board, you will have the Fourier transform of f when x is just f minus x. This is true. Okay, as L2 functions, but not pointwise.
Is it minus x?
Yeah. Maybe I'm saying something wrong here.
Is there a reason why, like an obvious reason why it is minus x?
It's just from the definition of things, it reflects the Fourier transform. If you take it, if you interact it 4 times, then it gets back to the identity. So you really have this operator f before this is right. Okay. Let me see. What I wanted to tell you is that, okay, so why is this map surjective? Well, I want to tell you this. So the image of L2 is closed because it's an isometry. Let us prove that it is dense. Hence, the whole L2. Okay, so if I want to prove that a subspace is dense, all I have to do is take a linear functional. So take a linear functional in L2 such that you apply to any guy in this image is 0, have to prove that the functional is 0. But who are the linear functions in L2? By the Rees representation theorem, they're just the guys in L2 itself. Okay, so that is a function f in L2, and assume that you have f scalar f of g being 0 for all g. How do you conclude that f is 0? The way you conclude that f is 0 is essentially by the multiplication formula here. You gotta be a little bit careful because this inner product now being complex this implies that integral of f of x, f of g of x bar dx is 0. But then this will become perhaps f of the inverse, the reflection of x, and then some there will be a slightly different operation that we have to do here. and then g of xi dxi. Okay, so essentially move the Fourier transform to the side. You might have to take a conjugate here or change the what's inside from xi to minus xi. So see, this f hat here is a combination of bars and changing the what's inside from plus to minus here. It's something that preserves it's an isometric operation. And then, so if you have that this is 0 for all functions g, what you end up proving is that this guy must be 0. So this implies that f of f is 0. Since f is an isometry, since the Fourier transform is an isometry, this implies that the original functional is 0. Okay? This actually proves that it's dense. So it's just a matter of applying the multiplication formula. Okay, so we have now that it's really an isometric isomorphism from L2 to itself. Okay, so it's injective, surjective, and it's an isometry. You have the multiplication formula. You have Fourier inversion. You have to be careful how to use it because the integrals defined in the Fourier inversion may not converge absolutely. So you may want to use Fourier inversion when you have integrable functions. And yeah, that's pretty much it. Maybe I could talk a little bit more about the Schwartz class after that, but I'll let you read. So what I suggest you do is that you take a nice book on Fourier transform, perhaps one of the books of Stein, and we have covered a little bit of the basics of the L1 and L2 theory. Now what comes next is to understand what's the Schwartz class and tempered distributions and what's the Fourier transform on a Schwartz function. So I want you to do a little bit of reading on that. I may have put 1 or 2 exercises in the homework about that if you want to take a look. Okay? So I think this is a good point for us to stop. Thank you guys for the attention in this class. I hope you enjoyed it and you have learned a lot of analysis here. All right, take care everyone.